Okay, so it gives me great pleasure to, I understand, inaugurate this room. Nice, intimate room. And to take part in this summer school of Bergswinnet and Dyer. What I would like to do today is, the title of my two lectures is The Mechanism of Kolyvagin System. And I'll try to explain where I want to go with it. Almost everything I will say is in a preprint with Karl Rubin called Kolyvagin Systems. And various versions of it are on various of our web pages, I think. Probably more organized on Karl's than mine. But to explain what I want to talk about, I'm going to start with a block diagram. And this is especially, I think, for graduate students who may have seen pieces of it, and in fact, one tends always only to see pieces of it in any given course or a series of lectures. But there's a whole, and I'd like to sort of situate where I want to go with Kolyvagin systems in my big diagram. So to begin, so this is a diagram of black boxes, and so the first one will be analytic number theory here. How many people can see this, by the way? In the back, you can see it. Okay. Now, by analytic number theory, I mean anything you mean by analytic number theory. For example, for the most part, L functions. So it could be Dirichlet L functions. It could be L functions of elliptic curves. It could be L functions of modular forms. Or it could be L functions in the Langlands situation. But you could imagine the simplest cases as sort of fitting perfectly well in the block diagram. For example, Dirichlet L functions. Over here, I want to put arithmetic. And by arithmetic, I mean quite exclusively things like, in fact, specifically Selmer groups. And you'll hear a lot about Selmer groups, or perhaps you have heard a lot about Selmer groups already. And Selmer groups are going to be nothing more than sort of very specifically controlled cohomology, pieces of Galois cohomology of Galois representations, and we'll get to them. And in fact, I'll define Selmer groups in my context when we get to it. But this you can think of as cohomology of certain Galois representations. Now, most of the interesting pieces of cohomology will be classifying very important ingredients in arithmetic. For example, for elliptic curve, it will be in some way controlling the group of rational points, the Mordell-Weil group of the elliptic curve. In the case of number fields, it will be controlling the ideal class group. And in general, we expect that we will have a sort of a fairly general theory of this arithmetic for fairly general Galois representations. Now, there's supposed to be a connection between these two boxes. And I'll put a question mark here because sometimes there is and sometimes there isn't. For example, in the most classical situations, there is something called the analytic formula. which connects a special value of an L function to the size of an ideal class group and perhaps other information. And these analytic formulas are in fact proved. But the whole point of this conference is to talk about the Birch-Schwinnett and Dyer conjecture and its various manifestations. And for that, there is certainly a big question mark. That is to say, most of what's asserted in the Birch-Schwinnett and Dyer conjecture is not yet proved. And if one goes further, one would have conjectures due to Bloch and Kato. And that's perhaps even less proved. OK. Now, so the bridge that we want to make is between analytic number theory and arithmetic. The way we're going to do it, or the way the general schema of doing it these days has evolved, is you first make a connection between analytic number theory and what I'll call algebraic treasures. Now, what do I mean by algebraic treasures? Well, if you're in a classical algebraic number theory situation, I might mean units. Units in number fields, circular units, elliptic units perhaps. If you're working with elliptic curves, specific collections of rational points that are very, very systematic and very well ordered. Heegner points, they're usually called. If you're working in higher algebraic geometric situations, you might have things that are now called Heegner cycles, algebraic cycles. If you're working in K-theory, as Kato does for elliptic curves, you might be thinking of very organized systems of elements in algebraic K-theory. But whatever they are, let's think of them as algebraic treasures. Now, the reason why I don't put a question mark between this and this, I just put a line, is that we're in very good shape here. That is to say, very often, if one has such an algebraic treasure, there will be a number that you can attach to it, sometimes a height, or sometimes a cuisine that you make out of these heights. And that number will connect to a special value of an L function. The most classical case of this is what's called Kroneker's second limit theorem. It's a kind of companion to the analytic formula in the classical case. A more modern connection is, the basic connection is due to Gross and Zagier. And this is the subject of, in fact, it's a kind of a mini discipline to make the connection to every time you have one of these, so to speak, algebraic treasures, to take some sort of evaluation of it and express it in terms of a special value of an L function in hopes of understanding something about the arithmetic. But so far, there is no connection between the arithmetic and the algebraic treasure. OK, now comes Kolyvagin. Now, what Kolyvagin does is he associates quite systematically to these algebraic treasures, well, the ones he's interested in, what I will call, well, what he calls Euler systems. Now, if you think of an Euler system as a collection, I'll just put it this way. It's a collection. Oh, God, I'm writing very small. Are we still OK? All right. OK, you, yell. A collection of cohomology classes. And I'll just say over abelian extensions of the base. Abelian Now, what cohomology classes, what collection, what abelian extensions, I'm not saying. But you have to think of this as a collection of cohomology classes, not over the number field, if you wish, or the base that you're started with, but over abelian extensions of that. The other thing I haven't said here is I have said that my arithmetic will involve Selmer groups, and these are cohomology classes. These are cohomology classes, but they're not of the same thing. They're cohomology of the dual. And that will be very important. Now, the whole point about this collection is that there are some coherence relations among these cohomology classes. Now, what Kolyvagin does is he has what he calls a derivative, well, I'll call it a derivative process, which, in terms of this block diagram, almost does, it's hard to say what it does, because it passes from a collection of such cohomology classes over abelian extensions to another collection of cohomology classes. But this time not over abelian extensions, but rather over the base field. You gain something because you have cohomology of the base. You actually lose something because the cohomology will be torsion cohomology. You'll have to divide the coefficient module of which the cohomology is being taken by various ideals in order to get this slightly better collection. And then all of the great applications of Kolyvagin's method simply go like this. You use these cohomology classes over the base to control this cohomology. That's my block well, almost my block diagram. Now, I might say a word about how you use it to control. You use it because these cohomology classes and these cohomology classes are for dual modules. And so you might imagine you use duality, and indeed you do. You use global class field theory, in other words, global duality, I'll call it GD, to make that control. Now, you might think that it's as simple as this, that if you have a vector space and you want to control the vector space and you know the dual vector space, you have pretty much control over the original vector space, especially if the original one is finite dimensional. And even if it's not finite dimensional, you have reasonable control over it if you know the dual. Now, that would make things easy, and I wouldn't actually have to give my lecture if that were the case. Here, the control is by duality, but it's a secondary control, and we'll see this. Now, there has been such an enormous collection now of classical and celebrated applications of the Kolyvagin process that one of the things I'm not going to do in my lecture is give any of the applications, and I hope that it will be filled in or has been to some extent filled in by other lectures, because I'm going to be talking about, in some sense, the mechanism of this collection of cohomology classes. I want to focus on that. Now, the thing that so to speak sparked my interest in sort of understanding this mechanism is when Karl Rubin and I sort of began looking at this collection, and there are some coherence relations, but it occurred to us that they're much more coherent than sort of previously noticed, or that is necessary to make this control. On the other hand, if you do, you begin to see things. So what we do is we sort of refine this collection, if you wish, or sort of understand the collection a tiny bit. And we get something which is somewhat more rigid than just a collection of cohomology classes, and that we'll call a Kolyvagin system. And one can prove that the classical Euler systems produce this sort of somewhat more controlled thing. So in some sense, I would put an equality sign here. The Kolyvagin system is sort of a fairly especially coherent collection of cohomology classes which does the trick. Well, it not only does the trick, as perhaps we'll see, but it makes so explicit the control here that you can reconstruct, in good cases, the module of interest, the Selmer group, almost, well, functorially from the Kolyvagin system. So there's a kind of functorial reconstruction. That may be less interesting than simply the fact that if you sort of understand this line and you want to make the circuit from here to here, the real issue becomes, start with one of the Euler systems. Does it give, and we will see that the Kolyvagin systems will be very rigid in some sense, and in the best situations there will be a best one, a single best Kolyvagin system, which will play the role in some sense of an L function, or a special value of an L function, but it will have values in cohomology groups. It will have an order of vanishing. It will have various invariants, which one can sort of pull out of its structure. And from that order of vanishing and invariance, one can reconstruct the arithmetic fairly easily. Or from the entire thing, one can sort of functorially reconstruct it. And so the real, let's say, sort of missing issue in this block diagram of trying to understand the passage from here to there might be to what extent does one have a kind of surjectivity here. Okay, that's my overview, and let me begin then with the oh no, there's one other thing I should say, that from now on I really will be talking only about this part of my diagram. I'll be giving the mechanism of this diagram. And to fit it into everything, you have to sort of fit it into the block diagram. Okay, so let P be a prime. I'll assume that it's greater than 2. Let's let R be a complete Noetherian local ring with a finite residue field of characteristics. Okay. My fields K, there'll be two sorts. At first they'll be local and then be global, and once I get to the real thing, they'll be Q. So K will be a local, non-Archimedean number field, or global. And as usual, I'll let GK be its Galois group, that is, say, the Galois group of K bar over K. I'll let M, or T as be my two letters, denote modules. So M will be an R module of finite type, finitely generated, if you wish. But endowed with a GK action, with GK action, which is both continuous and R linear. So those are my M's. And M star will be the dual. So M star is the Cartier dual, that is, say, the Hom of M into mu p infinity, the group of p infinity roots of unity that looks like QP mod ZP. With induced GK action, so I'll sometimes call it the Cartier dual, which is what it is. So it's again an R module with GK action. It needn't be of finite type, but whatever it is, I'll say it's of cofinite type. That is to say, if it's Cartier dual is a finite type, it is of cofinite type. Okay. I will be particularly interested in the one-dimensional cohomology of these gadgets. So I might call it H1Km or H1 or H1Km star. And to situate ourselves in terms of this block diagram, the Euler systems and the Kolyvagin systems will always have to do with this. That is, say, the m's that will appear. And the interesting arithmetic will always have to do with this. And so what we're going to try to do is control this by this. That's in the global case. In the local case, we'll have sort of a better luck, as you'll see. Can I erase this? You might want to have a few examples. And so the main examples really for R, these are examples that you might have in mind. FP is good. ZP is even better. And for people who want it, although I'm not going to emphasize it, lambda, the Iwasawa algebra, which I won't even define, is it's sort of in the wings. And I could also have R be as large as the relevant universal deformation ring, if one wants it. But we can keep our attention on ZP. And a typical M might be, well, M might be ZP itself with trivial GK action. It might be ZP of 1, that is to say, with the Tate module of mu p infinity, with action by the cyclotomic character. It might be the Tate module of an elliptic curve over the field K. And then the M stars, of course, would be mu p infinity QP mod ZP, or the direct limit of the kernel of multiplication by p powers of p as nu goes to infinity. This being the principal Galois module whose cohomology or whose controlled cohomology will be the relevant arithmetic for elliptic curves. And this is the place where we'll try to control the interesting arithmetic that arises by taking Galois cohomology of this one. Okay. Well, we have a local story to deal with. I'm going to get rid of this block diagram now, but I'll return to it at the very end of the second lecture. The local story is, well, as everybody really knows, global number theory is 99% local anyway, as politics is 100% local, I suppose. But so let's let K be local non-Archimedean, and little k its residue field. Okay, now how much do we have to know about K? Very little for this, and I'm going to sort of give a streamlined version of what we have to know. Well, the first thing we have to know is that there's an exact sequence of Galois groups. The inertia group is a normal subgroup of the Galois group of K, which maps surjectively to the Galois group of little k. And this Galois group has a canonical generator called Frobenius. This is a free generator, free in the sense of profinite groups of GK. Since it's free in the profinite category, of course, one has a possible lifting, but there are non-canonical liftings. I'll never make use of any of them. And this is called inertia. Now, the only interesting number in here for us is going to be the order of k star. And it's an integer. And the only interesting part of the inertia group for us is going to be this. I'm going to take the inertia group. I'm going to abelianize it, quotient by its commutator. And then I'm going to divide by absolute value of k star powers. How could I write that? I mean, if one way of writing it is this. I could go tensored with z mod absolute value of k star z. Okay, now by local class field theory, one has that this is isomorphic to little k star, and that's, in some sense, the only thing we will need. Interpretation of this particular quotient, it's a small quotient of inertia. It corresponds to tame ramification, of course, because this order is prime to the characteristic. And it's, in some sense, the typical Galois group, in fact, the Galois group of any maximal abelian extension of capital K, which is totally and tamely ramified. That's what we get out of local theory. Let me give a choice, make a choice of such a thing. So let's let L over K be any totally ramified abelian extension, Galois extension of our local field of the appropriate degree, of degree this number. Okay, for what's going to happen in a moment, I'm going to make that choice. Choose. Given K, choose such. There are a few. And when K is QP, which is going to be our principal situation, there is a choice to be made, and that's the one I'll make. And it will be important that I do. It's QP of mu p. For when K is QP, this funny integer is p minus 1. And that is indeed the degree of that abelian extension totally ramified. Okay, that's, as far as I'm concerned, the end of my local story, except for the basic mechanisms of local class field theory, namely Tate local duality. So Tate local duality, which I will just write that way. I'm only interested in the one-dimensional cohomology, so I can take h1 of k m. And by the way, if you go to Milne's book, you'll discover that he does it in sort of complete generality. Really, m can be quite general. But for us, there's nothing wrong with our assuming that m is finite from now on. Or at least for a while. Well, at least for this. There is a pairing, and that's given simply by cup product to, and what I would put here is cup product, so it would be h2 of what m and m star pair to, that h2 of mu p infinity, or mu p, mu infinity. But that h2 by local class field theory is qp mod zp. And so we might simply say that there's a pairing which sends a pair of cohomology classes to the local invariant attached to the cup product. Tate local duality says these are finite abelian groups, and they're in perfect duality. The other mechanism that we need is something which I will abbreviate this way, Hochschild-Serre spectral sequence. Hochschild-Serre spectral sequence is a beautiful functorial way of beginning to analyze the cohomology, the local cohomology of M. So for any, say, such M and K, you have an exact sequence which goes like this. 0 goes to H1 of the residue field, let us say of the Galois group of the residue field, with coefficients in the invariance of M under inertia goes to H1 of Km. That's the capital Km is H1 of capital Km is the thing we're trying to analyze. And we analyze it by this subgroup and the quotient group, which we can also identify H1 of I with coefficients in M, but the invariance under the Galois of the residue field like that. Now this is a functorial exact sequence, which you're entitled to call up whenever you have a module which is a Galois module over one of our local fields. Okay. Now, let's go back to the big picture for a second. We're interested in global cohomology, not local cohomology. All of this is preparatory. Now, we'll take a global cohomology class and we'll put local conditions on this global cohomology class. We'll ask for each place of the field what happens when you take the global class and you restrict to the local cohomology at that place. And to put a condition on it is to require that the global cohomology class restricts to a good class in that local place. Now, here's an example of a collection of good classes. These are completely, in some sense, well, I'm just going to call these the finite classes. And these I'll call the bad classes. I'll call them the singular classes. So to institutionalize that, I'll call that H1 and little f, the finite classes in here. And I'll call this the singular classes. And you should be thinking perhaps that when I take a global cohomology class and I ask that it be, say, nice locally at a prime, I might require that its restriction in here actually lie in here, or that its projection to here be 0. Well, I want a little bit more freedom, and so the freedom is going to come this way. That is to say, this is pure terminology. This has nothing to do with mathematics. I'm going to ask for the possibility of more general local conditions than that one. By the way, this collection of local conditions, that something be in this subgroup, I'll just call standard. The more general local conditions, well, to be completely general, you can just deem any sub-R module in here to be good and the quotient to be bad. And if you do so, you just make your choice. And for that, I'll just put a capital F here to distinguish from the little f. And so a capital F Km in here is really any fixed choice of local condition. And of course, the minute you do that, you've defined the singular classes as the quotient, and there'll be a capital S here. Whenever I have such a thing, I'll call it an FS structure on M. It'll tell us how to impose those local conditions on the global cohomology classes, at least at this local field M. Now, when you have an FS structure on M and you have Tate-local duality, you see simply by dualizing, you get a similar exact sequence with H1K M star. And so an FS structure on M by duality gives you an FS structure on M star. So let's give a list of possible local choices of local conditions. Well, there's the standard one, but there's also something you might call no condition. That is, say you require nothing. You say that H1F is the whole thing. Of course, if everything is good, then nothing is bad. Or you could require full condition. That is, say you require that your global cohomology class restrict to 0 in this local field. That is, say you can require that H1F be 0, and then everything is good. Now, for what we're going to do, if you just think of the standard condition, the no condition, and the full condition, these are pretty much the repertoire of our conditions, except for one other, which I'll call the L transverse condition. And that's going to be the key to these more restricted conditions, coherent conditions on Kolyvagin systems. So I have to define for you this fourth possible local condition. Okay. So you recall that L over K is our chosen field, which is totally ramified, which is abelian, and is of order the absolute value of K star, the cardinality of K star. Okay, I'm going to define a sub-module, which I'll call H1T well, I'll call it transverse, and then I'll restrict. Then I'll just call it H1TR when I get going. Km, contained in here. And I'll define it quite simply to be the kernel of the restriction map to H1L. Okay. Now this L transverse condition is going to be used and be useful, really, only when M satisfies certain supplementary hypothesis. I'll call it supplementary hypothesis. And there are two of them. The first is that M as a GK module is unramified. That is to say, inertia acts trivially. And the other condition is that the absolute value of K star, this number, kills M. That immediately implies that if M is non-zero, then the characteristic of the residue field of K is different from P. Okay. So under these supplementary hypotheses, I want to state the basic facts of life about these four conditions, really. So let's suppose that M is finite and satisfies those supplementary hypotheses, and let me state a proposition. I'll call it basic local proposition. And it has four parts. First, well, let me get the right order here. Okay. So the first is about H1 little f. That's the standard guy. So H1 little f of Km is canonically isomorphic to M, quotiented by Frobenius minus 1 times M. The second is H1 little s of Km. That's the standard guy. Tensored with K star, little K star, the residue field, is also canonically the kernel of Frobenius minus 1 in M. M is unramified, and its absolute value K star times M is 0. and finite, of course. Okay? And then the third is we have H1 transverse. So H1 transverse for Km, which is, of course, a sub-thing in H1 Km, can be projected to the singular part of the standard Fs structure, H1 little s of Km. And so we can consider the composition. So 3 says this composition is an isomorphism. This is an isomorphism. Okay, from 3 you immediately get, of course, that H1 Km breaks up as a direct sum of H1 finite and H1 transverse. Hence the name transverse. In other words, under these supplementary conditions, you have a factorization. And then the fourth statement is that both Fs structures defined by the finite, the standard one, and the transverse one are self-dual under Tate local duality. So F S, the F as finite singular structure, and TR as finite singular structure are self-dual. I should point out that, of course, that the no condition and the full condition are interchanged under Tate local duality. Okay. Let me try to prove at least a bit of this, depending upon time. I'll try in any case. One just comes from condition 4 just says that the finite singular structure of little f and of transverse are each self-dual under Tate local duality. Okay. For one, well, one has to see what one has. One has H1 little f Km. That M is unramified by my supplementary hypothesis. And so therefore, this is just H1 of the Galois group of the residue field with coefficients in M. And a cocycle here, if I evaluate such a cocycle on Frobenius, so if I take a cocycle representing an element here and I evaluate on Frobenius, I get an element of M. But that element of M is not well defined because I can change my cocycle by a co-boundary. And when you do, you discover that the change may be affected by an element in Frobenius minus 1 times M. And so the passage from C to C of Frobenius reduced mod Frobenius minus 1 times M gives you the canonical isomorphism. This one is perhaps a little more delicate. So let's start with H1 SKM, which, if you remember, is H1 of the inertia group with coefficients in M, invariant under the Galois group of the residue field. I'm going to write that in a more convenient way. That is, say, kernel of Frobenius minus 1. Okay. Now, M is unramified. And so, therefore, the action of ion M is trivial. And so therefore, h1 of im is hom of I into m. So I can write this as hom of I into m, kernel of Frobenius minus 1. Now let's take another look at this I, which is homing itself into m. Of course, hom of I into m, any homomorphism of I into m is abelian, factors through the abelian quotient of I. But m satisfies my supplementary hypothesis, and so therefore it is killed by the absolute value of little k star. So it factors through the abelianization of I divided by absolute value of k star powers. Now, in my little local story, I pointed out that that is canonically isomorphic to k star. So it's hom of little k star into m, a kernel of Frobenius minus 1. OK, once you put it that way, you see that Frobenius really doesn't act on k star. It acts trivially on k star. And so I can pull the Frobenius minus 1 into the parenthesis, hom of k star into kernel of Frobenius minus 1 in m. Well, I'm almost there because I'm not interested in this. I'm interested in this tensored with little k star. So if I tensor with little k star, I have h1 of s capital Km tensored with little k star is canonically little k star tensored with hom little k star into the kernel of Frobenius minus 1 in m, which maps, because m is killed by the order of little k star, that maps, and little k star is cyclic, that maps, that's canonically isomorphic to the kernel of Frobenius minus 1 in m. OK. I'm going to leave off on proving 3, but it's quite easy. It's not a no, maybe I'll prove 3. Depends on my time. Leave off on proving 3. The way in which you do it is you reinterpret it, again using Hochschild-Serre as the cohomology of the Galois group of L over k into m, and then you look at what that is, and it turns out to be nothing more than this. OK, so that's our basic local proposition. And in terms of that local proposition, we can produce something which I'll call the FS isomorphism, or homomorphism first. OK. OK, now I want to suppose about m my supplementary hypotheses that I've already supposed, namely that m is unramified and is killed by the order of k star, little k star. But 2 other hypotheses, namely, I want it to be free of finite rank, of course, over R. And I want, therefore, I can compute the determinant of 1 minus Frobenius acting on this free R module. And I want that to be 0. So these are even more supplementary hypotheses. I can sort of repackage this by taking the characteristic polynomial, which I'll call p of x, is the determinant of 1 minus x times Frobenius acting on m. And that's a polynomial with coefficients in R. And I notice that p of 1 is equal to 0. I also notice, by the way, that p, using Cayley-Hamilton, that p of Frobenius inverse kills m. OK, since p of 1 is 0, I can divide by the polynomial x minus 1 in R. And that division is unique. That is to say, p of x is equal to x minus 1 times a polynomial q of x, which is unique in R. So q of x is now a polynomial in R brackets x, which has an interesting property. Namely, q of Frobenius minus 1 times Frobenius minus 1 kills m. So one way of saying that is q of Frobenius minus 1 maps m. I want to write it. Well, I need more board. Maps m to the kernel of, well, I could put a Frobenius minus 1 there, but that's the same as putting Frobenius minus 1. But it also kills a piece of m, namely, it kills the image of Frobenius minus 1. Well, that's good. We've seen two canonical modules, two canonical isomorphisms with modules we know. And so we will now express this homomorphism as a homomorphism from 1 to 2. So I'll call this H1F Km, and I'll call this H1 singular Km tensor the residue field star. And I get a canonical homomorphism from the one to the other, which is this, but I'll call it phi fs. Finite, the fs homomorphism. And by the way, this is an isomorphism if this is free. Isomorphism if free. If the domain is free. If the domain is free, the range is free, and it's an isomorphism. We'll be especially interested in the case where this is free of rank 1. OK, that's our local story, and now we go to the global picture. So for the global picture, we're going to take K to be a number field. In fact, I'm going to take K to be Q. I'll let sigma be a finite set of primes containing the prime P. Generally, I'll denote by GQ sigma the Galois group of the maximal extension of Q unramified outside sigma. OK, now I'm going to have a bunch of modules, some of them free and some of them not. So perhaps I'll let T denote the free one. So T be a free R module, finite rank. With GQ sigma action, which is R linear. Equivalently, it's Galois module over Q, which is R linear, but which is unramified outside sigma. Okay. And of course, T star is the Cartier dual as before. Now, we want to put local conditions on the cohomology of T. We want to study, for example, the cohomology GQ sigma T. We want to study the cohomology GQ sigma of T star. This is what we're really interested in. This is the arithmetic. This is the control. This is how we're going to control it. But we're going to, and we have local conditions on this cohomology for all primes other than sigma. So now we would like to put possibly local conditions at sigma. So I will simply say a Selmer structure on the module T is a collection of local conditions at all primes in sigma. Selmer structure. And I'll still use the letter F for that, is a collection of local conditions, let us say FS structures, for all L in sigma. And I should say, by the way, that this is going to be, in some sense, low-tech Galois cohomology. That is to say, at P, it's not necessary to think, at least for the moment, of complex conditions, very difficult conditions. One can actually take no condition at P and get what I'm interested in explaining perfectly happily. Okay?
Do you take also conditions at Archimedean primes or not?
P is different from 2 and
yes, okay.
If P were not different from 2, I would. I'd just say if P were at 2, I would. Yeah. Okay, so now I can talk about what I'll call the basic Selmer groups. I should really emphasize that there are modules, so perhaps the basic Selmer are modules. As I said, there are going to be appropriately controlled pieces of Galois cohomology. So for T, it would be a subgroup of this. For T star, ditto, a subgroup of this. Now, I have a Selmer structure on T. And the basic Selmer group I'll simply label by the label of the Selmer structure. I'll put a little capital F there. And I'll just call it H1 capital F. And I'll put a Q here, T, to make it simpler. And that's going to be the controlled piece of the Galois cohomology that I'm interested in. And it's simply the ones that restrict to the good classes for all L and sigma. Or it's the kernel of the projection to the direct sum or the direct product of H1 capital S of QL, T, for all L and sigma. Of course, once I have a Selmer structure on a module, I have it on its dual, and so I can have the same story, but I have to put the dual Selmer structure on this guy, which I do. Okay. Now, again, these are the basic Selmer groups, or R modules. This is the one I'm interested in. This is the thing that contains the arithmetic. This is the thing that I'm going to use to control it. Okay? You have to keep your... I should also point out that this is a very, very nice situation in terms of change of various structures. For example, I could change sigma, I could change F. If I change sigma, I won't write this down because I don't have time, but if I change sigma and I put on the larger sigma, all the standard Fs structures, nothing has changed. But change of F is really interesting. Change. How does it behave on a change of F? Because it's the key to the whole Kolyvagin process. Well, for that, let's assume that I have two Selmer structures on the same situation, on the same Galois module T and the same sigma. I'll call one of them F1 and the other of them F2. And there's clearly an order relationship between Selmer structures. That is to say, you can ask for stricter or more lenient local conditions, and you have an order relation. And so let's suppose that F1 is stricter, if you wish, than F2. Well, then you certainly have that the Selmer group of F1, H1, F1, QT, I'll drop the Q after a while, is contained in H1, F2, QT. In fact, there's no need to have this Q. I'm going to get rid of the Q immediately because it's all over the place. H1, F1, T is contained in H1, F2, T. And what is the overflow? Well, the overflow goes like this. This goes to the direct sum of H1, F2, QL, T, for L in sigma, divided by the direct sum for L in sigma of H1, F1, QLT. Of course, I have the dual situation, and I have to reverse the 1 and the 2 here. So H1, F2 star T star goes to H1, F1 star T star goes to, well, you guessed it, and I'll just write it without saying it. Direct sum of, well, I'll say it. H1, F1 star QL T star divided by direct sum of L in sigma H1, F2 star QL T star. So I might call this I, and I might call this I star. Now, if you think for a second of Tate local duality and how we set things up, this is in perfect Tate local duality with this. Tate local duality induces a perfect pairing between these two. Okay, and the global duality, which I've been Tate, global duality, that I had signaled earlier this hour, is the statement that the image of I and the image of I star are orthogonal complements under this duality. Okay, now I can at least say a few words about the basic technique of Kolyvagin. The basic technique is this. You start with an F1, whose arithmetic you would like to understand. You would like to understand H1F, the cohomology with respect to the dual Selmer structure of the dual module. But you keep your eye not on this, but you keep your eye on that. And then you artfully increase, sort of relax the Selmer condition. That produces an increase here. If you can control this increase and you see how much you've got in here, then you can control the decrease here. You do it. Then you look around and try to increase some more. Constantly controlling the decrease. You finally discover here that you can't go any further. That means you can't go any further here. That means you've got 0. Well, then you tabulate the number of steps that you've taken, and you can compute, for example, the length of this module in terms of the number of steps it took you to go this way. Or if you're cleverer, you can compute certain invariants. Or if you're cleverer, you can compute functorially the entire group. But you have to deal with what one might call the jungle gym of these these local conditions where you it's an art. Now what we're trying to do is make it more of a science than an art. But it's an art. Now I have a feeling that, let's say in 10 years in the subject, it will be a thing, not an art. It'll be something you apply, a nice machine which does the trick. But you'll see that we will be sort of producing some jungle gyms in a moment, and in some sense more coherent ones. Okay. I can erase this. To prepare for this, you notice that I have an adjective in front of those Selmer groups, basic Selmer groups, because there are going to be other Selmer groups going through what I called the jungle gym in a moment. And in order to prepare for that, I need to give you a theory of quotients and twists. Okay. We're global. K is Q, in fact. And L is any prime which is not in sigma. And a break. Okay. Good. Oh, at least define the Selmer group the first hour. Okay. So when do we pick up again? In
11:30.
Excellent.
In 20 minutes.
Okay.